Hello and welcome back to part 3 of the PIC12F683 video series. In this part, we're going to start actually looking at the imagery we gathered during part 2 and studying the floor plan to better understand how the device is put together. I have uploaded all of the high-resolution stitches of every single scan. The link is in the video description. Unfortunately, I don't have a good place to host all of the raw unstitched tiles, but at some point I may be repost-processing them. My focus stacker is not the best, and I'm going to try and see if I can squeeze just a little bit more contrast out of some of the 100x shots. Before we get into the circuit analysis, one thing I do want to bring up, because I know people who are familiar with this are going to comment about it, and I know people who aren't may not realize what's going on. So I just want to talk a little bit more about some of both the hazards and mitigations of working with nitric acid and solvents. So first of all, I don't want to underestimate the risks. There have been a significant number of incidents. If you look up almost any university EH&S website, they've probably got an accident investigation of someone who mixed up the solvent waste and the acid waste containers in a fume hood, poured solvent into acid or acid into solvent, and an hour later the fume hood blows up. So this is a real thing. It does happen. There is significant damage and injuries that result. That being said, in this particular case, it can be done safely, and I just want to go over a little bit more about some of the design of the experiment and the process to minimize, but again, not entirely eliminate the hazards. So first of all, engineering controls, everything is being done in a fume hood, so you've always got as a minimum that fume hood sash between you and the experiment. Next is experiment design. Everything is being done at an extremely small scale. We're working with milliliters of acid or solvent in the big container, and any possible cross-contamination is at the microliter scale. So if we take a sample out of the acid and then put it in the solvent beaker, we're looking at microliters of acid remaining on it, interacting with milliliters of solvent. And conversely, when we take the sample after a clean, if we put it back to etch further and then add more acid, any residual solvent is going to be, again, at the microliter scale. So even if there was a significant reaction, it would be extremely small. Next is PPE. The lab coat I am wearing, as well as the gloves, are both fire retardant. There is a fire extinguisher in close proximity. I have never had any combustion or even visible aggressive reaction, but I am taking precautions just in case. Going back a little bit more to the experimental setup, another thing I'm going to mention is that the acid waste, and anytime I am decanting acid into a temporary beaker to inspect the sample, that's always set up on the left side of the hood, and anytime I'm storing solvent for cleaning or solvent waste, it's always on the right side. That's just my system. Everything is obviously labeled also, but just so I can't accidentally mix them up and pour things into the wrong one, I always know acid goes on the left, solvent goes on the right, and if I spill one, it's not going to get into the other. I'm not going to accidentally clean the sample on the wrong side of the hood because I've got the routine set up. And so, again, it is not perfect, but it's one more level of protection to minimize the chances of any unintended side reactions. Next, going a little more in depth on the experimental design. When we're doing the partial decap, so we start out with a clean sample of neither acid nor solvent on it. We add acid to it, we react it, and now we have a few microliters of acid on it. We take it over the waste beaker, and now we're flooding it with a large quantity of solvent. And this is part of the key here. Again, there is going to be a reaction. This is unavoidable. The goal is to keep that reaction from being dangerously energetic. And so the first way we do this is by the limiting reactant is the acid. We have, again, almost all of it has reacted. We have microliters of unreacted acid that limits the maximum amount of energy that can be released. And then simultaneously we are increasing the thermal mass of the solvent by flooding the sample with a very large quantity of solvent. And so the goal here is to carry heat away from this exothermic reaction at a much higher rate than is being generated, so it never gets anywhere close to the ignition temperature. And then when the cleaning is complete, we take the sample now covered with acetone, we put it back on the hot plate, and we don't apply acid immediately. We wait for the solvent to boil off. Again, acetone is quite volatile. It'll evaporate very quickly. You can see the sample go from wet to dry, and you don't apply the acid until that's done. And so this minimizes the chances of there being any reaction when the acid is applied. And then for the bare dye decap, it's similar. We decant as much of the acid as possible from the reaction beaker into the temporary storage beaker, pick the sample up with tweezers. We have at most 1 drop of acid left stuck to the surface of the sample and try to get as much of that out as I can on the beaker. So now we're taking this sample that has microliters of residual acid on the surface and putting it into a container that has milliliters of solvent. And again, the thermal mass of the bulk solvent is so high that even though there is a reaction, it is going to be slightly exothermic. It's never going to get anywhere close to the ignition temperature because of the ratios and the thermal mass involved. And finally, I do still consider that solvent waste stream to be somewhat reactive because there may still be some slow reaction going on after the temperature has gone down. There may still be some gas release and so on. I'm not expecting to get anywhere close to ignition, but there's still a chance that it could overpressure the waste container and cause a rupture and make a big mess and potentially a fire hazard if I've got solvent waste spilling over the inside of my solvent cabinet and leaking out of cracks and so on. And so to mitigate this, number 1 is I will add sodium carbonate to the waste stream after I'm done and let it fully react. So now I've completely destroyed any unreacted acid and we're at a neutral pH. There is still sodium nitrate in there, which is very slightly oxidizing, but it's not going to significantly react at ambient temperature. And the other is I just give it some time to stabilize and get any side reactions done before I go and put it away in a sealed container. I'll let it sit for 10-15 minutes at least and verify I don't see any gas generation. It's all sitting at room temperature, everything is stable, and then I will put it in waste storage. Anyway, with that out of the way, let's move on to actually looking at the device floor plan and getting a better understanding of where all of the key blocks of the PIC12F683 are.
So now that we've got a fully deprocessed device, we can start to understand the device floor plan. We're going to be looking at a couple of different images from different stages in the delayering process at different resolutions. So first off, this is the device overview at the top metal layer with a 20x objective. There's a couple of obvious analog blocks here, probably here, 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 here. And then we have what looks like a large memory array here, a smaller memory array here, a smaller one here, some kind of a floor plan logic block here, something here. But not a whole lot of details on what's what from the overview. Now if we look at this image, we get a much better idea of the device floor plan. This is after 27 etch cycles. The poly is still present in spots, contacts are gone, all of the upper metal layers are gone, and we get a really good understanding of how the device is laid out. Starting somewhat arbitrarily with the bottom center, there's a obvious memory array with some analog circuitry around it. Zooming in a little bit, we can see 14 large capacitors near the bottom, some analog circuitry here, and 14 identical tiles to the top, divided into a group of 6 and a group of 8 with a corresponding division in the memory array. This is consistent with this array being the main program flash. The processor has a 14-bit instruction word. It's a Harvard architecture with split instruction and data buses. And so perhaps what we're seeing here is this 8 bits is the low bits that are used when you're storing constants in program memory for indirect access over the data bus. And then this is the full 14-bit bus used for instruction fetches. We're going to take a more detailed look at the flash later on. For now, let's move to the left. Now we can see a second memory array. This one is significantly smaller, but the bit cells are much larger. There's a lot less analog stuff around it. And zooming in a little bit more, we can see this very textbook donut and I-beam shape, which is indicative of 6-transistor SRAM using a layout that was very standard out until about the 180 to 130 nanometer node, when another layout that was more friendly to modern lithography started to become popular. This is a 350 nanometer device, and so this is the exact SRAM bit cell layout we would expect to see. And again, we'll take a deeper dive at this later on, but for now we can move up to this array, which is a very small array of the same bit cells used in the main flash, and then has a bunch of other analog circuitry around it, and we can see 8 big capacitors down at the bottom here, also suggestive of high voltage generation. And so this is clearly the data EEPROM. Then moving up here, we see a couple of different small analog blocks. There's this one here, there's this one here, there's this one here. And looking at some of the partially deprocessed images, we can see polysilicon resistors were here before they were etched off. There's still one partially intact here, a bunch of big capacitors. So one or both of these blocks are likely related to the RC oscillator that is used when the external crystal is not connected. And this possibly this are likely related to the actual crystal driver, which uses the GP5 and GP4 pins, so that is this and this as the inputs, and so that is consistent with perhaps this being part of the analog circuitry for that, or it could possibly be one of these blocks down here. Moving to the right a bit, there's another obviously floor plan block, but this one is essentially all digital. What's interesting is down to the south, we see 13-way symmetry, and then one block that looks a little bit different. Again, 13-way symmetry, and then one block that looks a little different. The instruction word is 14 bits, and so I'm pretty sure this is related to instruction decoding. This might be latching 13 bits and then doing some pre-decoding on the MSB of the instruction. From my recollection, the high bits of the instruction word are a kind of a global mode selector that specifies a couple of different instruction formats, and so they might be beginning to pre-decode the instruction in the MSB as soon as it's latched. Then going up a little bit, this region here has 8-way symmetry. The processor has an 8-bit data path, and so this is probably the accumulator and main register path, and then probably additional ALU components. Down here is likely instruction sequencing. We can see what looks like some kind of a PLA or microcode ROM here. I haven't done extensive analysis of the CPU core yet, but I have heard that PICs of this generation were primarily microcode driven, and this is a 4 clock per instruction microarchitecture, so this is likely related to instruction sequencing. Next, moving to the right in this area, there are a series of identical copies of this same bit cell, which looks to have 2 possibly floating gate storage elements. There are some big transistors here with longer channels than the normal ones, which is suggestive of high voltage and some sort of NVM. And we have one column of 12 copies of this bit cell structure and one of 13. These are almost certainly the configuration register, which is commonly referred to as fuses, but these are not actually OTP. They can be wiped and reprogrammed as many times as you want. And so for a little bit of background, in modern devices, typically you don't have a dedicated configuration mode register as separate memory. It's far more common to have either a boot ROM or user software running out of flash will read configuration for the oscillators, your watchdog timers, your Brown detector, and whatever. And the first couple of instructions the CPU runs after boot will then take those settings and write them to latches of some sort that actually control the relevant circuitry. In older generation devices, it was common to actually have dedicated NVM cells that were hardwired directly to the relevant logic. And so that's why these bit cells are so big. And again, we'll deep dive more into this later on. But these are enormous compared to the flash structures because they actually have the entire programming and readout circuitry separate for each bit, so it can parallel read all of these bits simultaneously. And what's interesting is looking at the data sheet, the configuration word is 12 bits long. It's part of a 14-bit address space that's also used for programming the instruction flash, but the top 2 bits are unimplemented. So it makes sense that if we see a column of 12 configuration bits, that's probably this register. But looking to the right, the calibration word is also only 12 bits, and we see 13 fuses in the other column. There's 2 possibilities here. One is that there's an undocumented chicken bit for some additional feature that is not mentioned in the datasheet that's just permanently fused off. The other possibility is that it's entirely vestigial. One of these fuses may not be connected to anything at all, and it may just have been left over from an earlier version of the design and it was too late to change. But looking at the calibration word description in the datasheet, we can see the MSB is unmapped, and then we've got bits 12 to 0 are all defined except for bit number 5. And this is kind of an unusual place to have an unallocated bit. It makes sense to just have the MSB not hooked up if you're not doing anything. And so my hunch at this stage of the analysis is that this bit is not actually unimplemented. This is probably that extra configuration fuse, and we don't know what it does, but it's probably mapped at this location. So it might be instructive to try and actually program this bit in the calibration word and see what happens. Now moving to the right more and looking up a bit, we've got a bunch more analog circuitry around here. There's several different analog blocks in the device that are potentially related. GP0 and GP1 are the inputs to the comparator. So one of these blocks is likely the comparator. And then there's also a 10-bit A to D converter. And looking over here, we can see 10-way symmetry in this structure here, which looks like maybe output latches or something like that. So I'm thinking this region here, it's got a bunch of big resistors and capacitors, which does kind of give the vibe of an A to D converter, although I am far from an expert at analog CMOS layout. So I'm thinking this is probably at least part of the A to D. This might be related as well. There is also a voltage reference for the comparator, so somewhere in all of this is that, but we're going to be mostly focusing on the digital logic, so I'm not going to spend too much more time on that. Next, looking at the I/O pins, and again going back to the device pinout, we've got the VDD pin here, and note around here we've got protection diodes to the outer ring here, but not on the inner one. So that suggests that the inner ring is VDD and the outer is ground. It is very common on this generation of parts to have the outer ring be ground, so that's to be expected. And then looking over to the right side, we see no protection diodes on either side for the ground pin, but we do see a big grid of vias. And so, again, without looking at the intermediate metal layers, it's hard to be 100%, but this is certainly very consistent with the outer ring being ground and the inner ring being just not connected to ground at all because it's power. And then looking at the next pin down, which is GP0, there's an obvious analog I/O buffer circuit just inboard of the protection diodes. And looking at some of the other I/O pins, we can see very similar. It looks like some bigger, wider transistors. These might be for higher voltage tolerance, 5-volt inputs, and so on. And then some smaller, internally driven circuits. Then going down to the bottom left corner, we see again a fairly similar I/O buffer circuit here. But then this one looks a lot different. There's a lot more here, and there's some really, really big transistors with really wide channels, which is suggestive of this being designed to handle a higher voltage. And going back to the pinout, it's interesting to note that this is GP3/MCLR. And so the way that a lot of the earlier generation PICs with UV erasable EEPROM worked is they did not have an internal charge pump for high voltage generation because you had to use a dedicated UV box to erase them anyway. And so to program these, you would have to apply an external 12-volt power source from the programming device, and that would be used directly as the VPP for the EEPROM. And as they moved to newer generation parts, even though the high voltage for programming was generated internally by this charge pump circuit, it was common to still have high voltage required to enter the programming process, especially on the lower pin count parts. Again, this is only an 8-pin part. We've only got 6 IOs after power and ground. And so having to dedicate this pin to programming means you're losing 1/6 of your total IOs. And so what was very common was to have this pin being used as a GPIO in your circuit. And when you wanted to program the processor, you would unsocket it, put it into your programmer, and apply 12 volts to this pin, which would override the firmware and force the device into programming mode. And then you would be able to use the ICSP clock pins to clock your new flash in, erase the flash, and so on. And so most likely what we're seeing here is a comparator to check if a 12-volt signal is being applied to this input, and then if so, enter programming mode. And then a few other statistics that I haven't mentioned previously. The overall die size measured from corner of the seal ring to corner of the seal ring is 1.945 millimeters by 2.166, which comes out to 4.212 square millimeters. And the height of the standard cell rows is about 16 microns. The metal minimum pitch is about 1.77 microns, so this means we're looking at a 9-track high library. And also the basic 2-input gate is 5.88 microns wide, which comes out to 94.49 square microns. That's a density of 10.58 thousand gates per square millimeter, which is quite low by modern standards, but on the typical end of what I would expect from a 350 nanometer node. And finally, if we add up the total area of the actual logic regions, so all of this, and not counting any of the memory, not counting any of the analog, not counting any of the I/O, we get about 1.33 square millimeters of actual standard cell logic area, which if we divide this by the basic NAND2 cells area, gives us an estimated gate count of about 14.1 thousand. So again, very small.
And that's it for part 3. This was a short one. In part 4, coming out soon, we're going to have a recap of standard cell CMOS logic design and take a look at some of the actual gates in the device.